Thank you very much, Camille. It's a great pleasure for me to be here. I'm going to tell you a story about the relationship between hydrodynamics and quantum anomalies, and I hope that this topic is broad enough to be attractive to people. I want to start my talk with the discussion of what is hydrodynamics, and then I will jump to more modern topics of anomalies, how it was discovered within particle physics, and then I will talk again about somewhat the different topics called the gauge gravity duality, which, as Camille just said, was discovered 20 years ago. And combining these different pieces of information together, we will discuss something new that one can do with the very old theory of hydrodynamics, namely understand how quantum anomalies can affect the equations of hydrodynamics. There are many people who have contributed to these topics. What I will present to you here is somewhat a simplified version of the story. We trace out a single path in the stories with many branches and many people coming from different sides to the same problem. Hydrodynamics is a very old subject. The term itself, I think, was invented by Bernoulli in the 18th century. Now, when we talk about hydrodynamics, we mostly think about the Navier-Stokes equation that describe the time evolution of, in this case, non-relativistic fluid like water, starting from an initial condition. The equations of hydrodynamics then would consist of continuity equations, where rho is the mass density and v is the velocity of the fluid, and both rho and v can be a function of space and time. The second equation here is the momentum conservation equation, or sometimes it's called the Navier-Stokes equation. It tells you how the velocity of a small volume of a fluid changes due to different forces acting on this volume. For example, the pressure gradient, gradient of P, or the viscosity that give you friction between different neighboring volumes of the fluid. There is another equation that I didn't write down here, the energy conservation, which is important if one want to understand the transport of heat in the fluid. Amazingly, this very simple set of equations lead to many very complicated, beautiful physical phenomena. So, for example, one have turbulence if the configurations of the velocity of the fluid correspond to what is called high Reynolds number. One can generalize this equation to relativistic theories, and this has been done in the around 1930s. Instead of writing down these two equations that I have written before, we write here the equation of conservation of energy momentum and the conservation of some conserved currents, which in most cases can be taken to be the baryon number current. In the relativistic form, these equations looks very simple, so T mu nu is the stress energy tensor, and J mu is the current of the baryon number. You can see here there is a summation over indices, so you have 4 + 1 equations, 5 equations, which is much smaller than the number of independent components of the stress energy tensor, or the plus the current. To close the equation, one needs to impose certain conditions called sometimes the constitutive relations, which tell us the relationship between the current, say, and the density and the velocity. These equations reduces the number of independent components of the stress energy tensor and the current down to the same number of the same number of equations. one of the constitutive relation, for example, this one relate the current of charge, the baryon charge, with two physical effects. This rho v is the effect of advection. If we have a volume carrying density rho of that charge, moving with the speed of v, then there is a current rho times v. There is a contribution rho times v to the current. The second term is a bit more interesting. It is the term parametrizing diffusion. If there is a gradient of the density of certain charge, then one has a current that try to take charge from a place with higher density to a place with lower density. There is a similar equation for the stress energy tensor that would involve exactly these two types of terms, the advection or the inertial term, and the diffusion, which is in case the viscosity term. And again, this relativistic hydrodynamic equation finds applications in various fields of physics. In astrophysics, when one tries to understand the jet, highly energetic jet, we can use the hydrodynamic equations. And in a much smaller scale, when we collide two heavy ions with relativistic speed, we create a very small droplet of nuclear material, which during a very short amount of time evolve according to, we believe, evolved according to the relativistic hydrodynamic equation. I will spend a little bit more time talking about heavy ion collisions later on. All this is the hydrodynamic equations is basically a part of classical physics. So I was trying to understand, I was trying to do some research on where is when the first discussion of the quantum effect and hydrodynamics has been. And I think I found the beginning of the quantum hydrodynamics theory. The beginning is in a letter written by Kapitsa to Molotov in Soviet Union in April 1939. He wrote the following: recently, while studying helium near absolute zero, I found a whole series of new phenomena, possibly shedding light on the most mysterious area of physics. I need a theorist's help. In the Soviet Union, the theorist who knows the subject completely and whom I need is Landau, but he has been under arrest for a year. Can you ask NKVD to speed up Landau's case? If not, can we use his brain for scientific work while he is still sitting in his cell? Landau was released shortly after this letter, which is the second letter that Kapitsa wrote to the Soviet authorities. When he came out from the prison, you can guess which problem he started to working on. Exactly the problem of superfluid helium. And he wrote a paper, a famous paper in 1941, describing how a quantum theory, a quantum hydrodynamic theory of superfluid helium would look like. The way he derived this equation is slightly different. He has a very different perspective on the problem compared to the one that we have right now. He didn't believe, for example, in Bose-Einstein condensation, or he didn't believe that Bose-Einstein condensation is the explanation of superfluidity, but he knows that he can start with the Hamiltonian describing an ideal fluid, and by imposing certain commutation relation coming out from classical Poisson bracket of the classical fluid, he was able to build a quantum theory of a fluid. It was thought for a long time that quantum effect would exist only in superfluids, or at least in fluids where you have a reason to have a macroscopic quantum phenomenon. However, for about 10 years now, we know that quantum effect exists also in hydrodynamics of normal fluids. And these effects are related to something discovered in the 60s called quantum anomalies. It was almost an accidental discovery made through gauge gravity duality, surprisingly. So let me talk a little bit about particle physics with the emphasis on quantum anomalies. Pions is the beginning of particle, the beginning probably of the split between particle physics and nuclear physics is the discovery of the pion. Pion was first proposed by Yukawa in 1935 as a carrier of nuclear force. It was discovered in cosmic ray in 1947. There are three types of pions, pi plus, pi minus, and pi 0, where the superscript describes the charge of the pions. And here we will spend some time talking about the pi 0, which is which has a much shorter lifetime than the other two pions, because it can decay electromagnetically into two photons, while the other one has to go through a weak process to decay. The puzzle of pi 0 decay occupied some theories shortly after the discovery of the pions. There are two papers written almost simultaneously, one by Steinberger, which later won a Nobel Prize in physics. At the time, Steinberger was a theorist, and he was using the recently developed formalism of quantum electrodynamics to try to understand how a pion can decay into two photons. And there is a group of two Japanese theorists working on the same problem, and they came up with the same puzzle. Both of them could compute and the rate of pi 0 decay into two photons and get a result that matches very well with experiments. But in order to do so, they have to tweak the calculation. They notice that there is an ambiguity in the calculation. So this paper, for example, contains detailed discussion of that ambiguity. We have obtained a convergent but non-gauge invariant, non-gauge covariant result for the gamma decay of the mesons. Thus, in the present stage of field theory, we cannot give an unambiguous lifetime for the neutron meson. Depending on how the calculation is done, one can get a very small decay rate or a decay rate that corresponds to experiments. Steinberger also wrote that the method that he used, the Pauli-Villard regularization of the diagram, is not without ambiguity. So roughly speaking, the Feynman diagrams that has been computed is a diagram in which a pi 0 decay into two virtual particles, which at that time was considered as the proton and neutron, the nucleon, and then these particles emit two photons. I will not have time to go through the detail of the calculation, but roughly speaking, this integral, we have to do a one-loop integral which diverges. The divergence is similar to the divergence that one sees in this integral. There is the ambiguity in this integral. If I take integral of dx of the f of x plus a minus f of x, it seems that there are two ways of computing this quantity. In the first way, if a is small, one can do Taylor expansion over a and then rewrite the argument of the integrand as a times f prime of x, and the result would be a times the ratio of the values of f at plus and minus infinities. On the other hand, if we do in one part of this integral the replacement change of variable from x to x minus a, we will get the integral of dx of f minus f, which is 0. So this result can be non-zero if the function f has two different asymptotics value at plus and minus infinity, while this calculation gives us 0 all the time. Of course, it's very easy to understand the origin of this ambiguity. We are dealing basically here with minus infinity, with infinity minus infinity, and the way the result should depend on the way we compute this quantity. But the same ambiguity appears in calculation of something that should be a physically observable, the decay rate of the pi zero particle, and so it was very strange at the time. It took a long time for theorists to understand what's going on, and the first complete understanding of the puzzle of the pion decay was identified by Adler, Bell, and Jakiev in 1969. And the key point here is that in massless electrodynamics, the number of left and right-handed electrons are not conserved separately in the quantum theory, although if one tries to understand the theory classically, the left-handed particle cannot become a right-handed particle, and so the number of left and right-handed particles have to be conserved separately. So in order to understand how this effect can arise, let us consider massless spin 1/2 particles. So this is a very familiar object in particle physics. Neutrino can be thought of as particles whose spin has to point in the direction opposite to the direction of motion. It's called the left-handed particle, and the right-handed version, where the spin point along the direction of the momentum, is believed to be not the physical neutrino emitted in beta decay. In condensed matter physics now, we also have material which realizes similar polarization state of electrons. These are called Weyl semimetal, which I will mention a little bit later. The interesting thing would happen if we assume this particle to carry a charge. So let's now imagine that we can tune the mass of the electron to 0, or we go to a very high energy so that the mass of the electron can be neglected. An electron propagates, when it propagates, it can emit a photon, or this diagram can be also thought of as the diagram describing a motion of an electron in an external electromagnetic field. When we look at the detail of the process, we see that a left-handed electron can never turn into a right-handed electron if it's coupled, if the coupling is the coupling to a electromagnetic field. The right-handed electron should remain right-handed all the time. So chirality should not change. Chirality does not change when the particle moves in external electromagnetic field. But it turned out that this argument was too quick, and in fact, chirality is not conserved in quantum theories. By chirality here, I mean, say, the number of left-handed particles minus the number of right-handed particles. And this effect is the effect of anomalies. To understand anomalies, let us start with the quantum mechanics of a particle in a magnetic field. When we have a particle in a magnetic field, the transverse motion of this particle is periodic, and the motion along the direction of the magnetic field is infinite. So when we quantize the problem, we would see discrete energy level, discrete level corresponding to the periodicity of the transverse motion, and one continuous quantum number corresponds to motion along the direction of the magnetic field. So the energy levels of a Dirac fermion, massless fermion in a magnetic field look somewhat like this. These are the Landau levels, but of a relativistic particles. The energy spectrum is given by this formula, E square equal Pz square plus some constant times the magnetic field B. Here I have put various constants like h bar or c or the charge of the electron to 1. So this axis is the momentum of the electron along the direction of the magnetic field. At each value of Pz, there are various discrete energy levels, the Landau levels. The special feature of relativistic fermions are the existence of these negative energy level, which correspond to the negative Dirac C before we put in the magnetic field. These energy level, we believe, have to be filled like a Dirac C, and this would be an empty level. There is one level which corresponds to n equal to 0, which is rather special. This level is not degenerate like the other level. The other levels here, you can see I have used two different colors, one corresponding to left-handed particle, the other right-handed particle. Each level have each doubly degenerate with respect to left-right, while the n equals 0 level is not degenerated with respect to left-right. That's the outcome of the equation. The left-handed electrons have here the dispersion relation E equal minus Pz, in the other is E equal plus Pz. Okay, so now let's zoom in into this n equals 0 Landau level and ask the question, what would happen if we turn on both the electric field and the magnetic field? In the presence of the magnetic field, here we have the field state below 0, negative energy, and the empty orbital with energy larger than 0. Turning on an electric field, the momentum of the particle starts to change due to the Lorentz force acting on the particle. And so the momentum in this picture will move to the right. That means this red particle, the right-handed one, would move. I think I used the American convention on left-right. So the red particle move to the right, so they climb up in energy, and these left-handed particle move down because they want to increase their momenta, but the dispersion relation then tells them to go down in energy. So in this case, turning on an electric field even during a short amount of time would disturb the ground state, the vacuum, and we create two right-handed particles above the 0 level, and we create two holes in the left-handed spectrum below the Dirac, the chemical potential, which is 0 here. That means that we have non-conservation of the difference between the number of right and the number of left-handed particles. Doing the calculation more accurately, one can see that the rate of change of this quantity, n right minus n left, is equal to the scalar product of the electric field and the magnetic field. Well, the magnetic field here appears in a rather non-trivial fashion due to the degeneracy of each of the Landau levels. So that is the quantum anomalies, the non-conservation of a quantity that we thought to be conserved. But the story that I just told you sounds like a story of the Hilbert Hotel, which is completely filled, but we can put in one more guest by moving on the guest to the next room. That was the story. Is the story here similar to the Hilbert Hotel? It seems like so. We just moved the spectrum of right-handed particle on one side and claim that we now have two more particles in the right-handed sector. So basically here we have the problem of when we count the chirality, we have infinity minus infinity, which could be 0 or could be 4, depending on how we think about this problem. And the contribution of Adler, Bell, and Jakiv is to figure out the role of gauge invariance as a criterion that fixes the physical result. If we demand that gauge invariance we demand gauge invariance to preserve the conservation of usual electromagnetic current, then chirality is not conserved in the external electromagnetic field. So the full understanding of anomalies in quantum field theory is largely achieved by 1980s. There is beautiful connection to mathematics, to topology, but a possible connection between anomalies and hydrodynamics has gone mostly unnoticed, and there is a reason for that. It was noticed when a technique, very convenient technique for combining these two subfields was invented, which is gauge gravity duality. So gauge gravity duality was discovered 20 years ago. Maldacena wrote an article in 1997 pointing out on a possible duality between a quantum field theory and a string theory. The quantum field theory here is the so-called n=4 super Yang-Mills theory. And it is a field theory that, from the point of view of string theory, is the theory describing so-called a stack of n D3 branes. So these D3 branes are like domain walls or soap bubble in higher dimensional space. And the fluctuation of this object turn out to be describable as a string theory in a curved space called ADS5 cross S5 space, where the metric of that space is written here. It's broken down into a part corresponding to anti-de Sitter space, which is a space with constant negative curvature, and another part corresponding to a 5-dimensional sphere. So this duality then became a very valuable tool for people to study quantum field theories. And the reason is that there is a correspondence between some parameters between the two sides of the duality. On one side of the duality, the parameter is the product of the coupling constant G squared times the number of colors, NC. And this is the parameter that controls the expansion, the perturbative expansion in quantum field theory. And on the string theory side, this parameter corresponds to the fourth power of the ratio of the curvature of space and the string length. The string length can be thought of as the size of a string object, a smallest stringy object in the theory. The interesting thing about this relationship is that a very difficult regime in quantum field theory, the regime when G squared NC is much larger than 1, maps into an easy regime in string theory, the regime in which the strings becomes very small compared to the curvature. The curvature of space is small. The curvature radius is large. And string theory becomes gravity. So the duality maps a difficult regime in field theory in certain field theory into an easy regime in string theory. And using this duality, one can do various things. We can investigate field theory in the regime where no previous technique has been able to explore. So for example, one can try to understand gauge gravity duality at finite temperature, which would describe a supersymmetric version of the plasma of quark and gluons. So we take the gauge theory, in this case n=4 super Yang-Mills theory, and put it at finite temperature. And it turns out that it can be described by a black hole in the ADS space. And this relationship is very non-trivial. For example, the entropy of this plasma of particles is equal to the entropy of the black hole, which has a geometric interpretation. Around 2001, with Giuseppe and Andrei Starinets, I've been studying the relationship between black holes and quark gluon and the plasma and finite temperature field theory. One thing that we have figured out is that one can map the viscosity of this plasma to a certain classical object in gravity theory, namely the absorption of cross-section of gravitational waves by a black hole. So we found, for example, that in a large class of theory, there is a non-trivial relationship between the the viscosity that appear in fluid dynamics, the entropy from thermodynamics, and the Planck constant. So the ratio in this class of theory, the ratio of the viscosity over the volume density of entropy is always given by the same constant, h bar over 4 pi. And surprisingly, it turned out that in the real quark-gluon plasma that was created and studied in the relativistic heavy ion collider, the ratio eta over S seems to be very close to the one that one gets by doing calculation through ADS-CFT correspondent in a supersymmetric theory. So many facts, other facts about hydrodynamics was reproduced in black hole physics. For example, one can create a solution in gravity that corresponds to a turbulent flow in hydrodynamics. But there is one small problem which was noticed accidentally in 2007. So that was, this author considered a mostly academic problem of a rotating black hole, a certain solution that people know exactly, and they are trying to just interpret the known solution in gravity in the light of fluid mechanics. So they found that this rotating black hole can be interpreted very nicely as a fluid rotating on a sphere. And there is a match between black hole thermodynamics and fluid thermodynamics. The black hole solution is known exactly. The fluid dynamics solution is not known exactly, but can be is known as an expansion over the size of the sphere. And they were trying to match these two sides, and they found that the match works almost perfectly, but there is a small mismatch. There is this, you have to do the fluid mechanics in the limit of large radius of the sphere. So the match works to order 1 over the radius. Here it's a radius times the temperature. But while black hole thermodynamics has a correction of order 1 over Tr, the fluid mechanics equation seems to suggest that the first correction is actually 1 over Tr squared. There is a mismatch between the correction. And this discrepancy remains unresolved for 2 years until about 2009. It was identified that this mismatch is due to a new term in the hydrodynamic equation of n equals 4 super Yang-Mills theory. This new term was never seen before and was never considered before. And this new term is this term that we have to add to the current. So the n equals 4 super Yang-Mills theory have certain current. One can think about that as a transport of a certain charge, and one can identify it in this current advection part, a diffusion part from black hole physics. But there is another part that corresponds to the current along the direction of rotation of the fluid, as if you rotate the fluid, there is a current. Now, this term is not forbidden in parity because of the feature of the theory. The fermion is chiral. All the fermions in this n equals 4 super Yang-Mills theory have rotate in one direction. It's left-handed fermion. But this term seems to be very strange, even it's allowed by symmetry. If this term appears in hydrodynamics of the fluid that we are used to, for example, water, we can try to do the following experiment. Let me take a cup of water, which is here, and then let me drop sugar into that cup of water. We know that sugar comes in two different chiralities, right-handed sugar and left-handed sugar. I'm pouring them in together, and let's imagine that we can rotate this cup. Now, if the effect that I have just described to you on the previous transparency is real, then the two types of sugar molecules move slightly in different directions. That one move up, the other move down, and we can separate the two type of sugar this way. But this is very strange from the physical perspective. If we think about a molecule of sugar as a little screw, then when it rotates in water, it will have a propeller. It moves like a propeller and move in one direction. But if we rotate a cup of water, at the end, all these molecules will rotate with the same velocity as the surrounding water. So there cannot be any propeller effect. Another stronger objection to this term is that there is no mention of this term in volume 6 of Landau-Lifshitz or in any of the 10 volumes. And if one traces back why people haven't thought about these terms, it's not because, it seems that it's not because this term breaks parity. People thought about hydrodynamics where parity is not a symmetry before. But the main argument is based on the existence of entropy, the second law of thermodynamics. And tracing the derivation of different terms appearing in hydrodynamics, one can show that only shear viscosity, bulk viscosity, and a charge diffusion constant or thermal conductivity can appear in hydrodynamics. So I will show you a little bit of animation of what one would do with relativistic hydrodynamic equations to derive this fact. One take the two equations, conservation of energy momentum, conservation of charge. If you are not familiar with this equation, it's fine. I want to just demonstrate that one just do very formal operation, very familiar with people, for people doing hydrodynamics. Multiply this equation by certain, by the velocity, and this equation by the chemical potential, summing them up, and then from that we can identify entropy current whose derivative has to be positive, and the positivity of the right-hand side dictate that in the current in the stress tensor there could be only that many freedom. Only shear viscosity, bulk viscosity, and the thermal conductivity. So it seems that the holographic or this gauge gravity duality suggested something else, that there is new terms, somehow missed by this calculation. So at first, with collaborators, we try to Piotr Surówka, I try to understand if the calculation in gauge gravity duality is wrong. It turns out that it's very easy to understand that it's not wrong. One starts with some theory of gauge field and Einstein gravity with the Chern-Simons term in 5 dimensions, write down the equation of motion, and then try to specialize ourselves to a certain solution that corresponds to a flow of the fluid. And then from this new term in the equation of motion that comes from the Chern-Simons term, inevitably we get an effect that there is a current of this conserved charge directed along the rotation axis. So after that, we went back to the argument that one can read from Landau-Lifshitz and repeat it. Actually, we found that if we carefully follow the Landau-Lifshitz argument for positive entropy production, we came to a conclusion that the vorticity-induced current is not only allowed, but is required if the anomalies is present. There are some modifications to the hydrodynamic equation that one has to make. For example, certain current, the derivative has to be non-zero if the fluid is put in external fields. By doing everything very carefully, we find that these new terms has to be there. And what is interesting is that the coefficient of these terms are related to this triangle diagram similar to the diagram describing the decay of the pion to photon. And we found that the anomaly reproduces the correct value of the coefficient in NQ4 super Young-Mills theory that was found in gauge gravity duality. So the story here is similar to what was many times appears in physics. Sometimes we have experiments that show us a new effect, and then we theorists try to explain it. Except here that the people who showed us a new effect are not experimentalists, but people who pretend to be experimentalists. They are trying to move a fluid on a sphere using gravity, and then we, looking back in the theory, the second law of thermodynamics, we find this coefficient have to be non-zero. If we now put our system to a magnetic field, we find a similar effect. A similar effect occurs in a magnetic field. If we have a gas of massless fermion, a left and right-handed fermions, it turns out that there is a current if we have simultaneously a magnetic field and the axial chemical potential. The chemical potential for the difference of the left and right-handed fermions. So here the notation is the following. B is our magnetic field. Mu A is the chemical potential of the axial charge. And J is just our usual electromagnetic current. Okay. And let me explain to you again in a very simple picture how this effect can be understood just if one knows the solution to the Dirac equation in an external magnetic field. Okay. So let me let us remind ourselves that we have a spectrum of Dirac fermions in a magnetic field. Here the axes are Pz and the energy, and there are two special branches of dispersions corresponding to the n equals 0 Landau levels. So here's our left-handed particles, and here's my right-handed particle. In the absence of the chemical potential, I would have to fill all these energy levels below E equals 0. So there are these other Landau levels look like that, which I will not pay any attention to. I have this state filled, and all the state above empty. This is like a Fermi, a Dirac sea in the presence of the magnetic field. Now, if I have the mu axial chemical potential means that I have two different chemical potential for the left-handed particle and the right-handed particle. So, for example, I have here a higher chemical potential for the right-handed particles compared to the one for the left-handed particle, and the difference here would be called mu A in the formula. Okay, so here are my field particles. So these particles move to the right, and these move to the left. Clearly, you see that there is an imbalance in the current. There are more particles moving to the right compared to the number of particles moving to the left. And so that means J, the electromagnetic current, is non-zero. First, it has to be proportional to mu A. And secondly, it has to be proportional to the degeneracy of the Landau level, which is B. And so here, that's the very simple explanation of what people now people now call the chiral magnetic effect. The effect of having a non-zero current in the presence of an axial chemical potential that distinguishes different chiralities of the particles. There is a mysterious effect in relativistic heavy ion collisions that might or might not be related to the chiral magnetic effect that I have just talked about. When we collide two nuclei, which can be, in the case of Rick experiment, would be gold nuclei. In LHC, for about a month in a year, people do experiments with collision of two lead nuclei. A lot of times, the two nuclei collide with non-zero impact parameter. And so when we have these two nuclei passing through each other at some impact parameter, one creates a region of hot material, which is believed to be non-spherical in shape. And one can actually identify from the decay product which events correspond to zero impact parameter, in which event corresponds to non-zero impact parameter. And by concentrating on the event with non-zero impact parameter, one see an effect that the two, if we take a random pairs of the pion, the two pi plus particles tend to move in the same direction, or with angle less than pi over 2, while if we have a pi plus and a pi minus particle, they tend to move into opposite direction. So this effect was unexpected because most of the models of production of particles involve certain randomness in the generation of particles. So we create pairs of pi plus and pi minus, but they would move randomly in different directions. And there is no correlation between two pions of the same charge or with different charges. And one of the explanations that people have been trying to has proposed is that if the quark gluon plasma was created in the beginning with the asymmetry of the number of left and right-handed quarks, then we have a non-zero chemical potential for the axial charge. And when two ions, which are positively charged particles, move with non-zero impact parameter, we have a magnetic field due to this non-zero current. And this magnetic field would lead through the formula J equal mu A times B to an electric current and led to the observed effect. However, alternative explanation exists, and there are also some measurements. For example, recent measurement at the LHC that suggests that even in a collision of a proton and a lead ion, one sees similar effect. So it's not, at this moment, this is one of the competing explanations, but by no means a definitive explanation to experimental observation that definitely is, has been confirmed many times. Now, there are also another class of systems where similar effects in principle can be observed. These are solid-state materials, which three-dimensional materials, where the energy spectrum of electrons is the same as the energy spectrum of the massless Dirac fermion. So these are versions of graphene, but in 3 dimensions. And in the case of, for example, of Weyl semimetal, we have 2 so-called Dirac cones that are the 2 points where the energy, where the valence zone and the conduction zone touches. And these points can be classified by chirality. In the simplest Weyl semimetal, we would have one left-handed Dirac point and another right-handed Dirac point. And the low energy theory describing this material should look almost exactly like electrodynamics of a massless electron coupled to electromagnetic, coupled to photons. What is interesting about this material is that if one is lucky, the effects of anomalies may be visible in a transport measurement, very simple measurement. One of the quantity one can measure is the dependence of conductivity on the magnetic field. And here one can argue that the anomalies lead to a negative contribution to magnetoresistance. So let me explain why this negative magnetoresistance appears. It appears through a combined action of anomalies and the chiral magnetic effect. So the anomalies, as we said, is the creation of axial, that left minus right, axial charge due to the electromagnetic field. So in quantum field theory, we have d rho a over dt is equal E dot P. But in a real material, we would have relaxation of this charge due to various quantum processes. For example, the presence of impurities may lead to the processes transferring electrons near one Dirac cone to another Dirac cone. And so we would have to put in this effect by a relaxation term in the equation. So there is minus rho a divided by tau, where tau is some relaxation time. So solving this equation in the asymptote, when we turn on both E and B, wait certain time, rho a would saturate to a level, to a value equal to E dot B times the relaxation time, tau. Okay? But now we know also that presence of a charge density of the axial charge leads to a current by the chiral magnetic effect. J equal mu A times B, ignoring all the coefficients, that's 1 over 4 pi squared, etc. And that mu A is equal to the density divided by the susceptibility chi. And so here I have J equal tau B square over chi times E. So anomalies give rise to a contribution to the current that is proportional to B square. In other words, if one measures the conductivity as a function of the magnetic field, along the direction of the magnetic field, we should see the conductivity be having positive contribution, quadratic in the magnetic field. Okay, so here they plot the same quantity slightly differently. In the this axis is not the conductivity, but the resistivity, which is inverse of the conductivity. If this theory is correct, then we would see an effect that the resistivity would go down parabolically as a function of B square. And that is visible in a large part of the large range of the magnetic field. So this is the experiments done in Princeton on a material which I have to look up at the paper to say which one. There are many materials where similar effect has been observed. You can see here that although there is a negative magnetoresistance near B equal to 0, there seems to be some feature that is not completely understood. Another thing that I don't have a slide here, is the sensitivity of the magnetoresistance on the angle between the magnetic field and the electric field, which we also don't understand theoretically right now. The simplest theory here, if we assume if we put in a non-zero angle between E and B, the effect would scale like cosine square of the angle theta. In experiments, it seems that the dependence on the angle is much more, there is a much stronger dependence on the angle. So here this experiment is done with 0 angle. Okay, so let me just very briefly talk about what can think about the same effect in a more traditional approach, basically from the Boltzmann equation. If we have a gas of particles carrying spin, gas of particles, independent of whether they carry spin or not, we should be able to derive the hydrodynamic equation based on the Boltzmann equation. So Boltzmann wrote down an equation at the end of the 19th century. From this equation, we can derive the Navier-Stokes equation. So now that this derivation, when the particle carrying spin, when particles are relativistic and have chirality, are not very trivial. And there is a quantum effect from the Berry curvature that has to be put in very carefully. Basically, a particle that we have here have spin directing along the direction of motion. And when spin rotates, there is a Berry phase. And these particles collide with each other all the time. And during collision, the spin, since they are chiral, the spin has to be direct along the direction of motion. So there is a very non-trivial effect of Berry phase even on the collision term, which has not been completely understood. We understand, for example, that in an equation of motion of a single particle, there must be a new term that is described by Chang and New within the context of condensed matter physics, where the equation acquire a new term similar to the Lorentz force term, but involve a Berry curvature of this particle in momentum space. And for a massless Dirac particle, that Berry curvature is equal to the field of magnetic monopole in the center of the of momentum space. So this has been known for some years. These equations has been known. What is not very clear from this equation is how one can restore, for example, relativistic invariance. If we start from a purely relativistic theory, the kinetic theory written down seems to break Lorentz invariance. And again, this is one of the topics that there's some research has been done, but I think the final word has not been said. Okay, so let me come to an outlook. There are some interesting topics that I have not touched upon. There seems to be some interesting mathematical structure within hydrodynamics with anomalies. I talk a little bit about Berry phase in kinetic theory. There are applications in heavy ion and condensed matter physics, which I think still have to be done more carefully. And here we see a very interesting and fruitful cross-fertilization between different subfields of physics. Thank you very much.
Thank you for the wonderful talk. I wanted to ask about this measurements of chiral magnetic effect in the experiment. You mentioned there's this additional term, which is basically converting left-handed to right-handed, and more importantly, could we really say that in condensed matter there is an anomaly, since this Hilbert hotel is not really Hilbert hotel? There's a finite number of states now. Mm-hmm. So although it looks like mm-hmm. this effect, it's not really that. I mean, the origin is similar, but maybe at short enough time scales that the system doesn't have time to respond, you can sort of say that it's a chiral magnetic effect. I mean, is this additional term, what I'm asking, is this additional term basically coming from the fact that there is no really anomaly in this case because there's no Hilbert hotel, and the Dirac is finite?
Well, everything, of course, is finite. If we have a material, a real material, the two left, say in the wide semimetal, for example, if I have two Dirac points in a magnetic field, the spectrum would have to be connected somewhere here. So what we see in the measurements at small, if the electrons have small enough energy, we can approximate these electrons by level near the this point. And the effect is real, that if we turn on electric field, roughly speaking, the chemical potential here will be different from the chemical potential here. The system will go to a non-equilibrium state with slight imbalance. The fact that these two branches is connected down there is not important at all. The important thing is this new term would appear here because of that. But it's, if we take the point of view of low energies, quasi-particles, then we say the theory that describes our system consists of low energy degrees of freedom near these 2 points, and we get this quantum field theory. But these 2 points of view have to match with each other, and they do. Yeah.
Can I have a very brief follow-up question? So, do you think that maybe that term also exists in fundamental theories of in particle physics, and that we just, but it's some term at the Planck scale, and maybe it could signal new physics? Or has anybody explored that possibility, do you think?
I'm not sure what is the new term that you...
So that term does not appear in the calculation in quantum field theory, where there is an anomaly, where there is really...
the rho A minus tau?
Yes, rho A over tau, the
No,
term
rho A
which,
over tau,
right?
Yeah.
That appears in condensed matter materials. And you just wonderfully explained that it comes from the fact that everything in materials is finite.
No, it's not because of that. It's because this term is because you have what is that? The collisions with the defect or collision between electrons themselves that transport one electron to the other. In a pure material, that term would not be there.
Okay, good.
Yeah.
Giuseppe? You mentioned there are some alternative explanations for the charge separation in the heavy ion. What
are the other?
What are the, yeah.
Yeah, that's more detailed. I should know better. I don't. It's some kind of resonance. One of the explanations is based on the fact that you have decay of hadronic resonances, and these hadronic resonances have spin pointing along, preferably along the direction of the rotation of this fluid. So you have rho particles carrying momentum 1 that has spin on one direction, and people are trying to explain this effect using this picture. I think most of the time the calculation gives too small an effect to explain the correlation.
Thank you again for your talk.